Cooling. Fans. In the world of computer hardware, cooling is the constant battle against the second law of thermodynamics. Every piece of silicon, from the processor to the voltage regulators, generates heat as a byproduct of electrical resistance. If that heat isn't moved away efficiently, the hardware will throttle its speed to save itself, or in extreme cases, suffer permanent physical failure. The anatomy of air cooling. The most common way to cool a computer is through a combination of a heatsink and a fan. This is known as active air cooling. The heatsink. This is a block of metal, usually aluminum or copper, with dozens of thin fins. Its job is to provide a massive amount of surface area for heat to spread into. Heat pipes. In high-performance air coolers, you'll see copper pipes running through the fins. These contain a small amount of liquid that evaporates near the hot processor and condenses at the top of the fins, moving heat much faster than solid metal alone. The fan. As we discussed earlier, the fan's job is to blow cool air across those fins, stripping the heat away and pushing it into the case for the exhaust fans to handle. Thermal interface material, thermal paste. Even the most expensive cooler will fail if there is a microscopic gap of air between the processor and the heatsink. Air is a terrible conductor of heat. To bridge this gap, a technician applies a tiny amount of thermal paste, also called thermal interface material, or TIM. This paste fills the microscopic imperfections in the metal surfaces, ensuring a perfectly solid heat bridge between the chip and the cooler. Technician's warning: applying too much paste is messy, but applying too little is dangerous. The goal is a paper-thin layer that covers the entire integrated heat spreader, IHS, of the processor. Liquid cooling, the AIO. For high-end workstations or systems running local AI models, which can keep a CPU at 100% load for hours, liquid cooling is often preferred. The most common version is the all-in-one AIO cooler. It uses a pump sitting directly on the CPU to circulate a water-based coolant through flexible tubes to a large radiator mounted to the computer case. Fans on the radiator then cool the liquid before it loops back to the processor. Benefit: liquid can absorb significantly more heat than air, and it moves that heat directly to the edge of the case where it can be exhausted immediately. Risk: while rare, a leak or a pump failure can be catastrophic. A dead pump means the liquid stops moving, and the CPU will overheat in seconds because there is no fan sitting directly on the chip to provide emergency airflow. Case airflow mechanics. Individual fans are only effective if the airflow pattern of the entire case is logical. A technician generally follows the front-to-back or bottom-to-top flow rule. Intake: fans at the front and bottom pull cool, fresh air into the case. Exhaust: fans at the back and top. Since heat naturally rises, push the heated air out of the case. The dead zone: if your cables are a rat's nest of tangled wires, they create pockets of stagnant, hot air. Proper cable management isn't just about looking clean. It's about ensuring the air has a clear, unobstructed path from the front intake to the rear exhaust. Passive cooling. Some components, like low-power CPUs or the chipset on the motherboard, use passive cooling. This is just a heatsink with no fan attached. It relies entirely on the general airflow inside the case to move heat away. If your case fans are failing, these passively cooled components are often the first to overheat and cause system instability.